All right, so these are the results that we'll be needing today, okay, when we discuss statics. Okay, so now let's go to our discussion of statics. And let me first throw out as a motivational example, okay, a problem that we want to solve. Okay, all right, so I have a robot. Okay, it's a window washing robot, say. Okay, and here it is, pushing up against the window. Okay, I wanted to apply a force, okay, against the window. Some force. Okay, to make things simple, let's suppose the robot's not moving. Okay, it's static. Okay, and I want to apply a certain force against this window. Okay, now the question is, what should the torques be at my joints in order to apply the desired force? Okay, so very basic question, right? I don't want to push too hard. Window might break. I don't want to push too soft. It's not going to clean properly. Okay, so what should these torques be here? Okay. All right, so very basic question. Okay, so this is what we're going to answer today. So you can see what the generalization of this is, right? So we might now have a arbitrary spatial chain, okay, arbitrary spatial chain, and we want the end effector to apply a certain force. Okay, so what should the input torques be? All right, so that's the question we're going to answer. Okay, so what should input torques tau 1, tau b, tau 2b to generate a tip force F. Okay. All right. So in order to answer this question in its most general form, okay, in its most general form, we're going to have, right, an n-link spatial chain. It can apply forces in 3 dimensions, in 3 directions, okay, 3 independent directions, and it can also apply moments. Okay. All right. So the first thing we need to do is cover moments. Okay, now most of you in this class probably are familiar with moments and forces, but let's review it anyways. Okay. All right, so let's. Okay. All right. So if we have some rigid object, okay, and some forces being applied, say that way, okay, then this force is going to cause this object to move in some way. Okay. Let's suppose the center of mass is over here. So let's use their standard, this symbol, to denote the center of mass. Okay. Now, as long as the center of mass is not on the line of action of the force, so here's the force, and here's its line of action. Okay. So if the center of mass is off this line, what's going to happen to this object? There's going to be some rotation, right? Okay, so that's what the moment captures. Okay. Okay, so there's going to be some rotation. All right, so how do we capture that? Well, what we do is let's call this center of mass C. Center, let's write that, mass. Okay, now I'm going to draw a vector from the center of mass to the point at which the force F is being applied. Let me call that R sub c. Okay. Okay. Now the moment about this point C is then defined to be what? It's RC cross F. Okay, that is, it's a cross product of this vector R sub c with the force F being applied. Okay. All right. So if there's a moment, there's going to be some rotation. Now, if the center of mass happens to lie on this, on the line of action of the force, okay, then you can see that this is going to be 0. Okay, so there's going to be no moment. All right. Okay, so you can define the moment with respect to the center of mass, but in fact you can define the moment with respect to any point. Okay, so if I have some point, say here, let's call that point P. Okay, then I can define another vector from point P to the point at which the force is being applied. Let me call this R sub P. Okay, and I can similarly define the moment with respect to the point P simply by, let's write it maybe up here. Okay, so M sub P is RP cross F. Okay, so the point I'll make here is that moments can be defined with respect to any point. Okay, the point can be a point on the object. It can even be a point here, a point anywhere else. Okay, all right. So when a rigid body is motionless, okay, we say it's in static equilibrium. Okay. Okay, rigid body is in static equilibrium. Okay, so just think of it as being completely motionless. Okay. That's a now a rigid body is in static equilibrium when all the forces applied to the rigid body sum to 0. And all the moments applied to the rigid body sum to 0. Okay, so let's write this. Sum of the forces equals 0. Okay, and important, and sum of the moments equals 0. Okay. All right. So important thing. These moments, when you sum the moments, make sure the moments are calculated with respect to the same reference point. Okay? Moments, okay, with respect to the same reference point. Okay? All right, so this is the basic equation that we're going to be working with. Okay, so I don't want to make a big meal out of it. You know, it's just sum of the forces equals 0, sum of the moments equals 0. Okay. All right, so rigid body is in static equilibrium when these conditions are met. Okay. A robot, what's a robot? A robot consists of what? A bunch of rigid bodies, a bunch of links connected by joints. Okay, so we'll say that a robot is in static equilibrium if all its links are in static equilibrium. Okay, so a robot, okay, thought of as a bunch of links connected by joints, is in static equilibrium. Okay, if all its links are in static equilibrium. All its lengths are in static equilibrium. Okay? All right, so simple idea. All right, so if you want to do a calculation, what would you do? Well, you have, let's consider a single rigid body. And there are a bunch of forces being applied to this rigid body. So you want a reference frame, okay? So let's fix our reference frame, call it the S frame as usual here. Let's fix our body frame here. Okay? And we have some forces applied. Some forces being applied. And we have, okay, we have to calculate the moments. Okay, so maybe you want to calculate the moment with respect to the B frame origin. Okay, in which case we need this vector. Let's call that R sub B. Maybe we might want to calculate the moment with respect to the fixed frame origin. Okay, could be. So we might also need this vector. Okay. All right. So to write down the static equilibrium condition for this, what we would do is we would first pick a reference frame, maybe the B frame. Okay. So we want to write sum of the forces equals 0. So let's just consider a single force. Well, all right, sum of the forces equals 0 and sum of the moments equals 0. Okay. So eventually we want to get there. So we could say F sub B is just, right, the force F in B frame coordinates. Okay. R sub B is this vector R sub B, okay, in similarly B frame coordinates. Okay, and then M sub B, the moment, would just simply be RB cross FB. Okay. All right. So here's where we're going to do things a little differently from what you've probably done in the past. Okay. So remember, we're gonna think in a six-dimensional way, right? So remember that's the philosophy that we've been espousing throughout the course, right? You know, it's not easy at first, but let's go to 6 dimensions. Okay, let's stop thinking in a 3-dimensional way, the old-fashioned way, and think in the new way, 6-dimensional way. All right. So moments and forces. We're not going to think of them as separate things. We're going to think of moments and forces as a 6-dimensional single quantity. Okay. So we're going to define F sub B as a single 6-dimensional force. Okay, so we need a name. We need a name for this 6-dimensional thing. So let's call it a spatial force. Okay. All right. Some people don't like this name because spatial implies 3-dimensional. I happen to think it's okay. Roy Featherstone is the person who first started using this, the spatial, terminology. So spatial velocity is actually a 6-dimensional velocity. Spatial force is a 6-dimensional force. Okay. All right. So get used to this idea. Okay. we're now superior beings, right? So we can now think 6-dimensionally. All right, so here's this 6-dimensional spatial force, okay? So we can say things like a rigid body is in static equilibrium if the sum of its spatial forces is 0. Okay? All right. So suppose you have another reference frame. Okay, so now we need, what do we need? We need to figure out, well, if we change reference frames, okay, how do the equations change? Okay, how do the moments and the forces change? Okay. All right, and why do we need that? Well, we need that because if you look at a robot, right, you have many links, okay, and sometimes usually it's easiest to describe a link in terms of its own frame. Okay, so now ultimately you have to add velocities, add forces, okay, expressed in different frames. Okay, so you have to know how to go back and forth between different frames, descriptions of forces and velocities. Okay, all right. So let's just work with the two frames B and S. Okay. All right. So let's consider f of s. Okay. M sub s, f sub s. Okay. Where we now have to define what m sub s and f sub s are. So let's do that here. Okay, so what's m sub s? Well, let's do f sub s. F sub s is just, I'm going to say it's the force F, okay, expressed in s-frame coordinates. Okay, and r sub s, okay, r sub s is now this vector, r sub s, expressed in, and you guessed it, s-frame coordinates. Okay, and then m sub s, the moment, is going to be rs cross f of s. Okay, so the thing to note here is that m sub s is the moment taken with respect to the s-frame origin, this point. M sub b is the moment taken with respect to the b-frame origin, this point. Okay, so they're moments taken with respect to different points in space. Okay, all right. Here's what we're going to do. We're going to find a formula that relates f sub b with f sub s. Okay, so find a relation between f sub b and f sub s. Okay, now this is going to, well, you have all the tools to figure this out. Okay, it's just a calculation. Okay. Okay, so let's start with f sub b and f sub s. Okay, so let's see. As I said, f sub b is the force F in b coordinates. F sub s is the same force F in s coordinates. Okay, so what's the relation? So what is f sub b in terms of f sub s? Okay, what do you think? Maybe a rotation matrix multiplied by f sub s? Yeah? No? Seems reasonable, I think. Yeah. So maybe it's, would you agree with that? Yeah, so think about it. There's this force F sitting in space. You write this force F in terms of the B frame, and you also write the same force in terms of the S frame. Okay? It's just a rotation, right? Okay, so I can write it this way. But I know the answer I want, so I'm going to write it in that way. Okay. All right, so same thing. Okay, so the f part is easy. Now let's calculate the relation between m sub s and m sub b. Okay, so to do that, let's figure out what the relation is between r sub b and r sub s. Okay, so what is r sub b here? R sub b is this vector rb in b coordinates. Yes, I'm sorry, I erased the picture, but let me just quickly draw it here. Okay, so here's this point P, point of contact. Here's the B frame. So I said this is r sub s, that's r sub b. Okay. Now, looking at this picture, should have some flashbacks. Okay. Remember we said there's a point in space. Okay. Write the coordinates for this point standing at frame B. Call that r sub b. Okay. Now the same point in space. Let's write the coordinates for that same point from the S frame. Okay. Call that r sub s. Okay. What is the relation between r sub s and r sub b? Now it's that, right? So remember we made a big fuss about, well, when do you multiply by a rotation? When do you multiply by a transformation? Okay. And in this case, you multiply by this transformation. Okay. Now, what do I mean by this transformation? Well, remember we agreed that this is going to mean RBS, RS plus PBS. Okay. All right. Now, also knowing the answer that I want, I'm going to write this in a slightly different way. Okay. Let me write it this way. R sub b is T SB inverse, okay, times R sub s. Okay, which is RSB transpose minus RSB transpose PSB 0, 1 times R sub s. And remember that we stick a 1 at the end here. So we could write it R sub b 1 is that. Okay, in which case we have R sub b is RSB transpose R sub s minus PSB. Okay, so this and this are the same thing, just written slightly differently. All right, so now I have R sub b, f sub b. Now I can calculate m sub b, which is rb cross fb. Okay, so from now it's just calculation. Okay, so let's do it. So this is, let's write down rb first. It's RSB transpose RS minus PSB. Okay, this crossed with f sub b, which is RSB transpose f sub s. Okay. Okay. Now we use our favorite properties. Okay. Cross product. Let's write it as a product of a skew-symmetric matrix times the vector. So put this whole thing inside a skew-symmetric matrix. Oops. Okay. Times RSB transpose FS. Okay. Next, what do? Pull out this RSB to the front, put an RSB in the back. Okay, so let's do that. Okay, so equals, there's an RSB transpose out front. And in the middle we have RS minus PSB in skew-symmetric form times RSB, okay, times RSB transpose times F sub S. Okay, so you can see these two things cancel. Okay, so they cancel. So this is RSB transpose RS. Okay, now let's clean this up a little bit. F sub S minus RSB transpose PSB F sub S. Okay. All right, now, what's this? RS skew-symmetric times F sub S. That's a cross product. Okay, that's RS cross F of S, which you agreed was M sub S. Okay, so this is M sub S. Okay. And now, again, knowing the answer in advance, the answer that I want, PSB in skew-symmetric form. Okay, so if we take the transpose of a skew-symmetric matrix, what do we get? We get it's negative. Okay, so let's put a transpose and change the sign. All right, so then here's what we get. So this is equal to RSB transpose times M sub S, okay, plus RSB transpose PSB times F sub S. All right, so let's identify what we've learned so far. So here's relation 1, and here is relation 2. So this is M sub B. Here is relation 2. Okay. All right, so have a good look at it. Let's write it down in 6-dimensional form. Okay, so let's write this part down first. Actually, I'm going to erase it. Okay, actually, let's write the moment part first. So here's M sub B, here's F sub B. Okay, so this is equal to something times ms plus something times F sub S. Yes? Ah, yes, there's a transpose here. Okay, thank you. Okay, M sub B is RSB transpose here. And then F sub S is multiplied by RSB transpose PSB transpose. Okay, and F sub B is RSB transpose times F sub S. Okay, all right, so that's what we have. Does it look familiar? Does it look like something that you've seen? Maybe not. What if I do this? What if I do that? But I need a big transpose here now. If I do that. Aha, now it's starting to look a little bit familiar. Okay. This is what? R, R, P, R. Okay, it's the adjoint. Okay. So what we've essentially shown is that F sub B, okay, is the transpose of this adjoint map. It's this add T S B, but there's a transpose now. Okay, applied to F sub S. Okay, or if you prefer sort of the more explicit matrix notation, we can write it this way. Or F sub B is, remember this matrix, add TSB. So this is the 6 by 6 matrix, transpose. So this is this times F sub S. Okay, they mean the same thing. Okay. All right. So we see that the adjoint comes up again. Okay, more precisely, this time the adjoint transpose, okay, comes up again when we talk about forces. Okay, now recall V sub S is add TSB V sub B. Okay. All right, so we see something rather interesting here. Velocities transform according to the adjoint. Forces transform according to the adjoint transpose. Okay? All right. Now, you might be a little bit thrown off by the fact that, wait a minute. This is SB. We have an S here, right? So the way I remembered these formulas is, right, if the two B's are next to each other, they cancel, leaving me with an S. That's why I have V sub S, right? So this kind of might throw you off here, okay? So the way to rationalize this in your mind is, there's a transpose. So the transpose, you can think of as kind of switching the B and S around, okay? Switch around, so then the S's cancel and you're left with a B. Okay, so transpose, think of qualitatively as the S and B being switched. Okay. All right. So you have this relation for velocities, this relation for forces. Okay. All right. So remember, this applies for if you have any two reference frames, okay, A and B. All right. You want to describe the spatial velocity in terms of frame A and also in terms of frame B. This relationship holds. You can replace V sub S by V sub A. Same thing with this relation. Okay. You have some forces being applied to a rigid body, a spatial force being applied to a rigid body. Okay. You can express that force with respect to frame A or with respect to frame B. The relation is given by this, okay, where S is replaced by A. All right. So here's the transformation rule for spatial forces. Okay. All right. So next thing we want to do is we want to now consider virtual work. Okay. So Let me start